Well, here's a big question. Can you have current in a wire without a battery or plugging it in with some other source of voltage? And the answer is yes. But we didn't know it until this guy here, Michael Faraday, came up with Faraday's law in 1831. So yes, you can have current without some source of voltage or battery. Here's how. An electric current can be produced in a circuit by changing the magnetic field. This is called Faraday's law from Michael Faraday. Now keep in mind, if you have some kind of electrical wire, I'll draw one right here, you may remember that there is a current that is going around it. And you may remember we use the right-hand rule to determine the direction of that current. So, according to Faraday's law, you can produce a circuit by changing the magnetic field. You already have a current going through here, but you can make it bigger, you can make it better. In fact, you can seemingly make it from nothing, although it's not true that you actually do make it from nothing. But you are able to change a magnetic field and produce a current. Now let's see how we can do that. It's a process that he called electromagnetic induction. You're inducing a current. You can see the word induce here. That's to get something, to draw something out. Let's say we have here a coil or loop made of copper. Could be other things, but copper, of course, is a good one. And you have a magnet. Magnet, something that can hold a current. If you are to take this magnet and bring it toward the coil or loop, and even put it in the coil and loop, you will create an electric current in this coil or loop. Now these wires coming to it are not plugged in. This is not creating the current here. This is just into a galvanometer to register what the electricity is. And as you put in the magnet, you will have a register of electricity. And you can see here as we have an example of it, looks a lot like an electromagnet. You have this magnet that is in here, and you have the coil around it. Now what's happening, the coil is going in one direction, the magnet is going in another. You see the magnet is going left and right, the coil is going up and down. And that's very important. A circuit running parallel with this copper wire cannot hold a current. So if the direction of this magnet were, say, up and down, right next to this wire, it would not hold a current. You see, you have all these magnetic field lines coming out from the ends. And whenever you have the magnetic field lines coming out from the ends like you do here, it is able to close the circuit, I guess you might say. But if you have the magnet up and down, say it were right here, then these lines that are coming out of it, these magnetic field lines coming out of it, just do not seem to work. They do not seem to make the connection. And you may remember you have to have a circuit that is closed to be able to have electrons to flow all the way through and create electricity. Now I know this is kind of a heady thing, that this is a little bit complex, but let me try to show you something to make it a little bit simpler. Here's what you have. You have the same setup, copper wire, and you have this magnet that is going in and out. Now it registers nothing whenever it's a little bit farther away, but whenever it starts going put inside this tube of copper wiring, you can see right here what's happening. This is where you are getting a reading on the galvanometer. You're getting, in this case, volts. Now what happens, you have to have the movement. You have to have the movement. Remember, it's changing the magnetic field, like Faraday said. You can't just put the magnet inside and expect to continue to have changes in the magnetic field. You see here, when you bring it back out, you also have a reading, not zero. You have the reading that is going in the other direction. And like I said, if you were to have the magnet going straight up and down, you would not have any reading. It's kind of like it's too far away, just right here. So you have to, and you'll see it in just a little bit, you have to have the movement to change the magnetic field. If you're changing the magnetic field created by, let me put it, yeah, created by this magnet, if you are changing that magnetic field, then that's when you can produce that electric current. Now, in order to do that, we have what's called a generator. Now, you guys probably have heard of a generator, and when you go buy a generator at some Lowe's or Home Depot, it's not going to look exactly like this. This is kind of at its basest, most simple form. So, generators convert mechanical energy to electric energy. Now, my mechanical energy is just what you're doing. For example, here you have this crank. If you were to turn this crank, and you can see it says in this direction, you're actually doing some mechanical, some physical energy. How can you make that physical energy into electric energy? Well, you have this set up right here. You have these wires, and if you notice, these wires are connected through the tubes here, but they are connected. They can create a circuit, and they're in between these ends of the magnets. This is a north and south right here, and I guess it could be either way, and in fact it will be, and you'll see later on how. But as you turn it, you are changing the magnetic field. So that will create the energy. Now let me show you what it will look like here. You have the same setup here. This is being turned. Notice we have a north end here, a south end here. By not only turning it, but by changing the polar ends of the magnet to this, here you have made the north end the south end, and here you have made the south end the north end. Now notice what happens. You have this which has already come in a loop to here, and once it gets through half its rotation, the magnets change and force it to turn and go the other way. And notice what here, it's still going the other way, it's still going the other way. The south and the north have not changed until you get to right here. Whenever it is even, the south and the north will change, which will then in turn make it go this way. And here's where you can see it has started going back this way. So you have an alternating every half turn direction that this copper wire is going. It's alternating every half turn, and it creates electricity the entire time. And notice what's happening here. Whenever you start out, you have a positive current here and negative current here, and eventually it will change. It will change once you end up having that flip from the north to the south here. So this is what's called an alternating current. An alternating current, AC is for alternating current. The outlets you have in your home and for most of the world are alternating currents. As the wire rotates, it alternates between being perpendicular and parallel to that magnetic field that we just saw. And when the current continues from its stop, that's when it alternates. Now, what's the difference between alternating current and direct current? By the way, AC, DC, that's where you've heard of that from. Alternating current is very similar to direct current, except direct current comes from a battery and it keeps flowing in that direction. But notice in alternating current, you have this apparatus. That's this apparatus that you saw, not here, but here. That's this apparatus right here, right there. That is the symbol for it whenever you get to something like this. Right there. So what you have an alternating current. As long as it's flowing one way, as long as it's turned one way, it will go this direction. But then when it flips the other way, it will go in that direction. It is an alternating current. It alternates from going one to the other. What in the world is that? I'll turn that off. But anyway, the outlets you have in your home, like I said, are going to be from there. Now let's talk a little bit about turbines and generators, something you've touched on before in a previous class. Turbines and generators turn, and they are attached to a core where wire is wrapped around a strong magnet. Here you have the wire wrapped around a strong magnet. Here you have steam, which is making the turbines turn. It could be other things like windmills, which are making the turbines turn in this area here. It could be a hydroelectric plant. Here you have the turbines. It is turning in the generator right here, and it makes the electricity right here. See, whenever you can turn the turbines, and you have the electric the coiled wire around the cylinder, you're creating that electricity. And turbines and generators do exactly that. The result is electrical energy. Now you have heard of an electromagnetic spectrum. The electromagnetic spectrum we actually studied in this class earlier this year. These have waves, well, they don't take a medium. All the other waves have to have a medium, and here's why scientists think that is the case. You know, we've studied electromagnets recently. It's similar to that. You've heard of electromagnetic spectrum. Those are waves that can travel without a medium. They are made of oscillating electric and magnetic fields. The electric field is this one that goes up. The magnetic field is this one that goes out. So electricity and magnetic fields are part of the reason we get that light from the sun, that visible light, the X-rays, the ultraviolet rays, the infrared rays. And scientists are thinking this is actually what's happening, that you have an alternating magnetic field and electric field that is actually coming to us from outer space, from the sun. Now let's talk a little bit about transformers. Transformers can change one alternating current to a different voltage. And transformers you may see are like this out at the street. But here's kind of the core of that, the basic part of that. You have a lot of wires here and a lot of voltage. With this magnetic flow here, if you put fewer wires over here, you will have a resulting lower voltage. Now here's where this comes in handy. When it's close to the power plant, you want to increase the voltage. But when it's about to come into your house, you want to decrease the voltage. And if you have more wires here, you can increase the voltage. Now let me kind of show you what it will look like as it put in reality. Here you have the generating facility, which has a lot of voltage, and it increases. Here's a transformer that increases it. It's called a step-up transformer. It increased the amounts of volts. Goes through the power wires in a lot of voltage, and then it is reduced once it gets to places like Walmart, Kmart, big buildings like that. Places where you buy your food, which need a lot of electricity. But when you get to your house, you don't need as much electricity. So you have another transformer here that tones it down. This one and this one are called step-down transformers. They reduce the voltage. The step-up transformers are used near the generation facility. The step-down transformers are used near houses and places where you would use electricity. Hey, I hope you've learned a lot about electric currents and magnetism.